Welcome to The Explainer. I am absolutely thrilled you're joining us today because, well, we're going to uncover a truly mind-bending connection. We're going to look at how a seemingly simple, totally chaotic physics toy actually holds the secret to understanding something as massive and, honestly, as stressful as the stock market. We're basically going to build a bridge between pure, unpredictable randomness and guaranteed mathematical order. It's going to be a fun one.
Okay, right off the bat, I want you to picture something in your mind. Just imagine 6,000 tiny metal ball bearings. Got it? Now imagine taking all 6,000 of those tiny balls and pouring them all at the exact same time through the top of a vertical, triangular board that's just packed with a maze of wooden pegs. It sounds like pure chaos, right? Just this absolute cacophony of metal bouncing absolutely everywhere.
Okay, let's dive into this because right here is the core mystery we are going to solve today. How on earth can the wildly unpredictable, entirely random movements of all those individual bouncing balls magically create an outcome that is practically guaranteed? Seriously, how do we get perfect predictability out of pure, unadulterated randomness?
All right, Section 1, the Galton board.
So, that device I just asked you to picture, it's called a Galton board, and the mechanics of it are brilliantly simple. Let's zoom in a bit and just track the chaotic journey of one single ball bearing as it falls. As gravity pulls the ball down, boom, it hits a peg. At that precise moment, well, actually, it's a strict 50-50 chance it bounces to the left or bounces to the right. Then it falls, hits the next peg, and faces another 50-50 chance, left or right. It literally repeats this at every single layer of pegs all the way down. In mathematics, this series of coin flip decisions is called a random walk. Because of this constant 50-50 splitting, predicting the exact final landing spot of any one individual ball at the bottom of the board is, for all intents and purposes, completely impossible.
And this brilliantly illustrates the absolute magic of this system. Just look at the stark contrast here. Over on side A, we have the micro level. One ball bouncing completely randomly, making it totally impossible to predict. But flip the board over and look at side B, the macro level. When you pour all 6,000 balls through the system together, they always, and I mean literally always, create the exact same predictable pattern at the bottom. Individual chaos somehow transforms into beautiful collective order.
Which brings us to Section 2, the normal distribution.
So, a collection of these random walks creates what we call a normal distribution. You've probably seen this before. Visually, it looks like a classic bell curve. But you gotta ask, why do the balls pile up in a massive mountain right there in the center? It's not magic, it's just probability. The balls clump in the middle simply because the middle offers the absolute greatest number of possible paths to get there. As a ball bounces down, combining different lefts and rights in various sequences almost always sort of guides you back toward those center bins. There are literally thousands of different path combinations that will successfully deposit a ball directly into the middle.
But now, consider the far edges of the board. Why are there so few balls way out there? Let's visually step through it. To end up in the bin on the extreme far left, what exactly has to happen? Well, the ball hits the first peg, and it has to go left. It hits the second peg, it must go left again. Third peg, left. Fourth peg, left. All the way down the entire board. There is literally only one highly specific path to end up on the very edge. When you compare that one exceptionally rare path to the thousands of paths leading to the center, yeah, you quickly realize why the normal distribution forms. The farther out you go, the fewer the paths available.
All right, moving right along. Section 3, modeling the stock market.
Now, here is where things get truly exciting. We are going to scale this mathematical concept up from a small physical desk toy to one of the most high-stakes human systems on the planet. To do this, we really need to meet a brilliant historical figure. Meet Louis Bachelier, a pioneer born in 1870. Long before modern computers or super complex algorithmic trading even existed, Bachelier was using advanced mathematics to model financial markets. And his absolute genius was that he looked at the wild, seemingly chaotic fluctuations of the stock market and essentially saw a giant Galton board.
Now, what's really interesting about this slide is how Bachelier specifically mapped the physical world of the toy directly to the financial world. It is a perfect one-to-one analogy. Think about it. In his model, the ball falling through the machine represents the stock price. Each horizontal layer of wooden pegs, that represents a single step forward in time. And the final resting place of those balls at the bottom, that normal distribution represents the expected future price of the stock. It's brilliant. So the crucial point here is how time affects predictability. Look at side A. After a very short time step, meaning the ball has only fallen through a couple of layers of pegs, the stock price can really only move up or down a tiny bit from where it started, right? The spread is incredibly narrow. But look over at side B. After more time has passed, meaning the ball is cascaded through dozens of layers of pegs, a much wider range of final prices becomes mathematically possible. The expected future price of a stock is always a normal distribution centered right on its current price, but the longer the time horizon, the more that bell curve spreads out and flattens.
And that brings us to our final part, Section 4, Radiation of Probabilities.
Get ready for a mind-blowing twist here, because this is where human finance connects directly to the fundamental laws of the physical universe. As Bachelier was formalizing the math to describe his stock market model, this spreading out of stock prices over time, he had a massive aha moment. He realized that the complex equation he'd just written out to describe the financial markets wasn't actually a new mathematical concept at all. No way. He had accidentally rediscovered the exact identical equation used in physics to describe how heat radiates away from regions of high temperature into regions of low temperature. Let that sink in. The math behind human greed, panic, and trading was the exact same math governing the thermal physics of the universe.
Let's move to the timeline and see how this builds across history, because it's pretty cool. Back in 1822, decades before Bachelet was even a thought, a scientist named Joseph Fourier first discovers that heat radiation equation. Then in 1870, Bachelet is born. As an adult, he takes this fundamental principle of thermodynamics from Fourier and brilliantly adapts it to describe the chaos of financial markets. It is a stunning timeline showing just how deeply interconnected our reality truly is.
And because his stock market model perfectly mirrored Fourier's physics of radiating heat, Bachelier gave his discovery this beautiful, almost poetic name, the radiation of probabilities. It's incredible to think about, right? Whether we are tracking a single bouncing metal ball bearing, observing the thermodynamic radiation of a hot iron, or trying to predict the future price of a tech stock, the underlying mathematics of the universe remain beautifully, perfectly consistent. It really leaves you wondering, if the chaotic stock market is just a giant Galton board, what other seemingly random parts of our lives are actually following a perfectly predictable path? Thanks for joining me for this explainer. Keep learning, and I will catch you next time.